Okay, so we'll pick up where we left off kind of last class. I posted that first Excel assignment. So when you're doing that, some of the questions might need like a written response. If you want to, you can upload multiple files. So show as much in all of your work in Excel and upload that Excel file for all the work that you do in Excel. And then anything that has like a written response, you know, it's kind of a pain. If I open Excel here. So it's kind of a pain if I'm writing sentences in Excel. I can't, made a mistake, but see kind of this text goes across multiple cells. So one thing you can do is with a home, there's kind of this merge, you can merge and center it, or you can just, if we go back up here, there, if I highlight this and right click, I can format the cell and do some things. If it's easier, just type it out in Word and you can upload two files. So upload your Excel file and your Word file. Some people will try, are okay writing in Excel because it doesn't matter how long this sentence gets, right? Even though I can't see it necessarily, like if I type, right, it kind of cuts that off. But as long as I click on that cell, I can still read everything. So you can do it in Excel, but if it's easier for you as you're typing it out, just do it in Word. Just do it in Word and kind of upload two files, okay? Any other questions kind of related to homework or anything like that in terms of kind of due dates or kind of expectations? We're okay with that? Let's see if there's anything, nothing on Zoom. Okay. So let's go in. We leave off. I'll open up this guy. So we talked about variance last class. We did some stuff with weighted variance and weighted means. So kind of a reminder of our weighted mean equation. So when we wanted to find this weighted mean, we simply multiplied every single group, right? This is when we had group data. We took the weight, we multiplied it by whatever variable we're interested in the value for that first observation, multiplied those two together, did that for every single observation, added them all up, and then we divided by the sum of the weights. Right, we went through a lot of examples. I showed you how you can kind of use Excel to do these calculations. We talked about the variance, how it's kind of a similar idea. It's just instead we take the weight and we multiply by that deviation squared. Okay, so today, I think we ended on, I said, you could do some of this on your own. Kind of, we worked through a couple of these to reproduce some of the answers. So this is where we left off, okay? So today, we're going to still be looking at this idea of group data, right? We'll get some more practice with it, but we're going to talk about it in a slightly different context, okay? I guess I'll put me down here for the video today. So remember when we were building those frequency distributions, we had to put things in bins, right? So this, is another example of that where I had satisfaction ratings of a certain product, and I don't know what the total is here. It looks like it's somewhere around 50 people. I was asking to kind of rate this product, right? What was their satisfaction rating? Okay. Now, there was 4 people who responded either 36, 37, or 38, right? Somewhere in that range. And there's 25 people who responded either 42, 43, or 44, right? Somewhere in that range, okay? So this is kind of like when we're building the histogram. This is actually kind of what you're going to do with that first Excel assignment. You're counting the number of observations that are within the range of each bin. So if that's the only data we could observe, so let's say we go back to the one that we worked on in class where we had the COVID data by state, but then I kind of put it into this frequency distribution. Let's say I couldn't see the original state data and all I see is this frequency distribution. Right? How can I still find the mean and the variance for this satisfaction rating variable? Okay? Well, we talked about last class, right? I don't want to simply, here, I don't even have values. I have ranges of values. So the first thing we're going to need to do is say, well, look, if I ever only have group data that comes in bins, I'm going to use the midpoint of my bins as the value for that X variable, right? The X variable is satisfaction rating here. But because it's a range, we'll use the midpoint. So 36 to 38, we'll use the midpoint of 37. 39 to 41, we use the midpoint of 40. So on and so forth. Okay. Now, I'll never give you an example where it's really, really difficult. So I think there's one of these on the homework, on the Connect homework. I'm never going to give you like 36.2 to 43.9. So then you have to, take the average. The midpoint should be pretty easy to identify, something similar to this example. Okay? So, if I'm trying to say something about the mean, and before we even talk about calculating it with this type of a data set, if I'm using the midpoints here, what do you think the mean is likely to be around? Maybe not exactly, but what is it going to be near? 40, 42, right? 43, 44. Like, if we're looking at where the majority of the data is, we're going to see where are the highest frequencies, right? Well, the most common response was to be between 42 and 44, right? The next most common responses were right on either side of that. And then very few responses were far from that kind of middle bin. So if I had to guess, I'm probably going to say somewhere between 42 and 44. Right? It might be a little bit higher than 44, might be a little bit lower than 42. Kind of hard to really get an exact idea just looking at the frequencies until I actually do the calculation. But it looks like the majority of the data is kind of right here in the middle around that middle bin of 42 to 44. Right? So how can I actually compute what the exact weighted mean would be? All I'm going to do, right, is use the frequencies as my weights. So remember before we had add up all the weights times whatever the value was for the x variable. Well, that's still what we're doing here. It's just our weights are the frequencies, and we don't have one value, we have a bin range, so we'll use the midpoint, okay? But once we have that, it's really the same procedure, right? We go through each observation or each group here, take the weight, which is now the frequency, so 4 times that midpoint of 37 plus 15 times that midpoint of 40, plus 25 times that midpoint of 43, so on and so forth. Once we add all those up, we then divide by the sum of our weights. Well, if our weights are now frequencies, we're just dividing by the sum of the frequencies. So really, this is just a notation difference. I mean, the actual computation, the process is exactly the same. Okay? Now, one thing to kind of mention here, something we can start to think about, and I know I mentioned this last class, but I want to kind of hammer it here. When I add up those frequencies, remember when we were doing that, those histograms or those distributions, we said hopefully we can check to see if we've done this correct by when we add the frequencies up, every observation should be counted in at least one of these bins. So when I add the frequencies up, I should get my, what? What should those frequencies add up to? Go back to thinking about when we were building those histograms, we said, if I've counted every observation once I add up all these frequencies, I should have the total number of observations, right? If every observation's been counted once, well, then when I add all this up, I'll have every single observation. So another way, we can think about the sum of the frequencies here. It's really the total number of observations that's in that data set that I can't see, right? All I see is this data set. But there was some original data that had every single person's individual response to the satisfaction rating. I can't see that data. Someone grouped it for me and then showed me that. But if I add up those frequencies, it would be the original number of observations in that data set before it got grouped, right? Or kind of the number of observations in the data set, we represent that with n, right? The size of the sample, okay? Any questions on that before we keep moving? Like I said, this is pretty similar to what we did last class. It was just kind of a little bit of notation difference and this idea that we have to grab the midpoint. Okay? Now the variance is going to be very, very similar as well. It's going to be very similar to that weighted variance we talked about. A couple things get replaced. Instead of using an x value, we only have midpoints now. And whatever that deviation from the mean is squared, we weight it by whatever the frequency is of that category. Right? It's really, you can think of the frequencies as weights and nothing's really changed here from what we talked about last class. The one thing that we have to be careful of is last class when I did these weighted variances, I treated it as population data, right? But a lot of times, when we have these histograms, we're building this off a sample data set. So this is not every single person who's ever used that product, right? It's just a sample. So instead of dividing by n, which would be the sum of the frequencies, we'll divide by n minus 1, which would end up just being the sum of the frequencies minus 1. Okay? So it's the same sort of principles that we were talking about before with population and sample variances. It's just now, in order to get that sample size n, we weren't able to just observe that, right? All we had was the group data, so we would add up the frequencies and then subtract 1. Right? Any questions on this? We'll look at this, the computation here in a second. So let's say I wanted to first find that mean. I kind of already talked through this process, but I would go through every observation, take the frequency for that group or that bin now, and multiply it by the midpoint of that bin. So 37 times 4 is 148. 40 times 15, 600. 43 times 25, 1,075, so on and so forth. So I get every single observation. I've done that for every observation. I then add up all those products, right? All of those frequencies times the midpoints. That would give me my numerator, right? The sum of the frequencies times the midpoint. And then the final step is for the mean, just divide by the number of observations. Well, here we said the number of observations, I can't observe that original data set, but I know I can get that number of observations by simply adding up all my frequencies, right? So here, if you want to think of the denominator, we could write in n, or we could write in the sum of the frequencies there, right? So sure enough, if we do that, we get exactly 43, right? Kind of that exactly in the middle of that band. It just so happened to work out that way. It doesn't have to be, but it did in this example, okay? So what if I want to do the weighted variance for this, right? Well, I would go through, find the deviation from the mean. We now know the mean is 43. So the very first observation, I'd take that midpoint, 37, minus that mean of 43, so -6 squared, that's 36. Then multiply by that frequency, 4 times 36, 144. I then go down to the next observation, its midpoint is 40. 40 minus 43 is -3 squared, which is 9, times a frequency of 95, 135, right? I go through and I do this for every single observation, and then when I'm done, right, this summation sign means I add them all up, right? I add up all those deviations squared times the frequency. And the reason why, if we remember, this variance is some measure of the average distance from the mean that the data is, right? So this bin is evidence that, you know, this midpoint is pretty far from the mean, right? It's what, 37 minus 43, we were 6 away, okay? But there was only 4 observations that were that far away, right? So it kind of adds a certain amount to our numerator of our variance. Notice once we get to this middle category, the midpoint of 43 minus that mean of 43, well, 43 isn't far away from the mean at all, it's exactly the mean. So this one bin is evidence that the data doesn't vary very much from this middle point, from this mean. So this bin or this observation doesn't add anything to the variance because it is evidence of no variation. Now, every one of these bins is either no evidence or some evidence that there's variation. So then when we add them all up and divide by the sum of the frequencies or the number of observations, we're kind of getting this average deviation from the mean squared, right? So we add all those up. We have our sum of the weights. The last step is we need to take that numerator, divide it by our, go back here, divide it by our denominator, which should be n minus 1, or the sum of the frequencies minus 1. So, whoops, I'm going to move myself here. So we take that 522 and divide it by the sum of our frequencies minus 1, or divide it by 64 here, okay? Any questions on this before we keep moving? Like I said, it should look pretty similar to what we did last class. What if I wanted the standard deviation here? What's the only other thing I now need to do? How do I go from a variance to a standard deviation? Remember, the variance we write as sigma squared. The standard deviation we write as sigma. So to go from the variance to the standard deviation, I simply we should know this. So we got to hammer this in, right? So to go from the variance to the standard deviation, it was only one additional step, which was to take the square root, okay? That applies no matter what we're talking about. The regular variance, once we get to the weighted variance, we'll talk about some things in the future, some other statistics. Anytime we're moving from any type of a variance to a standard deviation, all we're doing is taking the square root, okay? So here it would be the square root of 8.16 would be our standard deviation, okay? So we'll want to remember that for sure, okay? So there's no questions at this point. We'll move on to a slightly different topic, okay? We're good? Let me check here, nothing in the chat. So, oh, I just got paranoid, okay. So I just got paranoid that I didn't hit the record button. So we're not gonna do a ton with this kind of later on in the course, but this idea is important for us to understand, and I'm gonna take what we're gonna talk about here and show you something you'll probably see in other courses. So this is why I wanna cover percentiles, because you'll probably see it elsewhere. So if we think about percentiles, you probably have heard of them or been, experienced them to some degree. You don't have to as much anymore, but if you've taken the ACT or the SAT, they usually tell you what percentile you're in, right? So they'll tell you you're in the 90th percentile. What that means is that you're better than 90% of the other test scores that were submitted, right? If I'm in the 90th percentile, my test score was better than 90% of the other test scores. Or said differently, it was worse than 10%, right? If I'm in the 90th percentile, that means 10% of the test scores were higher than mine, 90% were below mine, okay? So how do we find let's say instead, I want to find out what percentile my score was. How are they coming up with this number? How do they know your score is better than 90% of the other test scores? Well, just intuitively, if I had every single ACT score in front of me, what does it kind of mean to be better than 90% of the other scores? Well, if I had them all arranged from smallest to largest, right, I would just find the score such that there was 90% of the observations below it and 10% of the observations above it, right? Excluding that one observation, right? So that's basically how we're going to calculate percentiles, okay? So I have this in here, maybe you've seen this before, but they kind of tell you what percentile you're in for your height and your weight, depending on your age. We've seen percentiles out there in the world, right? I always like this graph because there's like 50 things going on at once, and it's hard to decipher right away. But how do we actually come up with those percentiles, okay? So the first thing is, I kind of already mentioned this, we arrange the data from smallest to largest, right? Once we've got the data in front of us, smallest to largest, it's a little bit easier to figure out where the 90th percentile is. So let's say I had 100 observations. I'll align them from smallest to largest. They don't have to be the numbers 1 through 100. They could be, 50, they could be any number between 50 and 60,000, but I've got 100 of them. So when I arrange them from smallest to largest, the smallest observation will be in the first position. The next smallest observation will be in the second position, so on and so forth, right? So what position has the number that represents the 90th percentile cutoff? The way I'll find that position is this formula, okay? So whatever percentile I want, if I want the 90th percentile, P becomes 90 here, right? I just plug in whatever percentile I want into P, and N is the total number of observations, right? How many observations do I have in front of me? Once I put that percentile I want and the number of observations in this formula, it will tell me the position that the 90th percentile is in. So maybe, if I've got 100 values, right, it's going to tell me that it's, the value that's in the 90th position, right? That one's kind of easy because it's a nice, easy number of 100, right? If I have 100 numbers, I know that whatever is in the 90th position, that's the 90th percentile cutoff, right? Now, if I've got 1,321 observations, a little bit harder to figure out there. Okay? Now, sometimes it works out that this is just an integer. It's really nice and easy, right? I plug in the 90th percentile and it tells me, maybe I have a different size data set, and this tells me that the 90th percentile is actually in the 31st position. So I have all my numbers arranged, right? So I just go over the number that's in the 31st position, and that value would be what my 90th percentile cutoff was. So it's easy if this is an integer value, but what happens if it's like 31.2? Well, I don't have a 31.2 position, right? So we've got a little bit more work there. And I'll actually explain this a little bit more kind of just with some actual examples. But if we have that scenario, we're going to have to do something that we call interpolation. Where's the word? There it is, interpolation, right? So what does that interpolation look like? Okay, so let's say I've got 10 values. I will make it a little bit easier. And I arrange them from there, I don't know, these are metal funds values, so how much the metal fund was worth. So I arrange it from smallest to largest, right? Kind of the smallest being the largest negative values. I've got these all in order. I've got 10 observations, so my number of observations, n is 10. The percentile I want is that 25th percentile, okay? So I plug those values in, I get this into my calculator, and I get, okay, the 25th percentile is the value that's in the 2.75th position. Well, I've got a second position, I've got a third position, I don't have a 2.75th position, right? So anytime it isn't an integer, we're gonna have to do some interpolation. Okay? So the easiest way to think about this is, it's very similar to a weighted mean when we do interpolation. Okay? I am closer to what integer value here? Am I closer to 2 or am I closer to 3? 3, right? Not a trick question. So I know that the 25th percentile, the value will be somewhere between -7 and 8, but a little bit closer to 8 than it is to -7, okay? So what I'm going to do is, I'm going to use whatever that decimal is I see on this position and use that as my weight, right? The other weight would be what else, how would I get up to 1? Okay? So if 0.75 is my one weight, my other weight would be 0.25, okay? And if this was 2.9, my weights would be 0.9 and 0.1, right? So that's how I'm going to determine the two weights that I need to use, right? Now, how do I use those weights? Well, once I know that this is 0.75 and 0.25 are my weights, I'll weight the value that's in the position that I'm closer to with the higher weight, right? I'm closer to integer 3 here, so I'll weight that value of 8.09 with 0.75, and I'll weight the value of -7.3 by my other weight, which was 0.25, right? So that.
How did you get the second weight?
Oh, yep. Someone have a question?
Yeah, how did you get that second weight of 2.5?
Yeah, so we'll go back here. Anytime I see this position that's not an integer, my weights will be whatever that decimal is, and then whatever my second weight would be, what gets me up to 1. So you can think about it as the sum of these two weights will always be 1. And the way that you determine the first one is, well, what's this decimal? It's 0.75. So then the other weight has to be what gets me to 1, 0.25. Okay? So once I have those weights, the higher of the weight I use with the value in the position that this is closer to, right? So that value of 8 gets weighted by the higher weight, 0.75, and that value of -7 gets weighted by that lower weight of 0.25. Okay? Does that clear it up? Any other questions on that? Okay, I'll assume we're good there. Right, there's no questions on kind of how I would do that? All right, and this kind of makes sense, right? If the 25th percentile is closer to that third position, the value I get should have been closer to 8 than it was to -7, and sure enough, it is, right? It's 4. Right? It's a little bit closer to 8 than it is to -7. Now, it gets a little bit trickier, and I'll just kind of show you here on the slide. So what if I would have come up with 2.3? Right? Now what should my weights be?
0.3 and 0.7.
Yeah, 0.3 and 0.7, right? I look at that decimal, that gives me my first weight. My second weight is whatever gets me to 1. Right? Now, there, it's a little bit trickier, because now when I think about what position am I closer to? Second or third position. 2.3 is a little bit closer to the second position, right? So now that value in the second position should get the higher weight. Well, what was my higher weight? My weights were 0.3 and 0.7, so I actually would want to multiply this -7 by the 0.7 weight, and that value of 8, which was in the third position, which I was a little bit further away from, that's the one that would get that lower weight of 0.3. Right? And I don't know what this ends up being. My guess is it's something probably like -4, something, or -3, somewhere around there, right? A little bit closer to that -7 than it is to that value of 8. Okay? I can, I don't know what this is off the top of my head, and I don't have a calculator in front of me, but you can kind of imagine this would be pretty easy to enter into a calculator. What if it was, here, what's an easy one? What if I had 2.5? What would my weights be? It's not a trick question. What would my weights be here? I look at the decimal, 0.5 and 0.5. And that one's easy because really all I'm doing there is I'm just finding the average of those two, right? Yeah, that one won't happen all the time, but that would be a kind of an easier one. Is there anything else I want to say here? Oh, when I said that we're thinking about these as weights, so think about if we go back to the original one where I was looking at 0.75, my weights were 0.75 and 0.25. Now I said those weights, we only have two numbers, right? We're in between two locations. What did I say the weights always add up to? 1. So if I think about this as a weighted mean, here's my weights, here's my values. Well, why didn't I divide by the sum of the weights? Well, if the sum of the weights is always 1, dividing by the sum of the weights is never going to change anything. So technically, it is in that denominator, but we don't have to factor it in because the weights will kind of always add to 1. Okay. All right. Any questions on that before we keep moving? So now that we know how to find these percentiles, and here I think I'll just skip over this stuff for a second. Well, I'll mention this real quick. So we can find the 25th, the 50th, and the 75th percentile, right? We'll call these kind of our quartile cutoffs, right? First quartile, third quartile. Now the second quartile actually is also the median because remember, the 50th percentile would mean that value is higher than 50% of the observations and lower than 50%. So it exactly would split our data in the middle. So that second quartile actually represents our median, right? Then we kind of come up with this thing called the interquartile range or IQR. It's just the difference between that third and first quartile, okay? Now we're gonna do this thing where we calculate these upper and lower limits where we go, look at that first quartile and go 1.5 of the interquartile range below it. We get the upper limit by taking that third quartile and going 1.5 times that interquartile range above it. So what is this going to look like? So hopefully this works today. Waiting. All right, there we go. I think it's going to be straight. So we have this interquartile range that we calculated, which was just the difference between our first and our third quartile. Okay. So a lot of the times what you'll see, and maybe you've seen this I think marketing does this a lot in some of their research, but there's these things called, I mix them up. So it's box and whisker or kind of stem and leaf plots, but what you do is you first identify kind of where that second quartile is or where the median is, right? You then make a box. So I don't know, maybe this value is 50, right? That's the median, just happens to be 50. So you then make a box using the values for your second and third quartile, okay? I don't know, I'm just put some values in here just to make something up. Okay? So here's our box. So what are the whiskers, right? So the whiskers, we draw these lines that go up from the third quartile and down from the first quartile. The value that we stop at will be that third quartile plus 1.5 times the interquartile range. And then the lower limit, we said we'll use that first quartile and go 1.5 times the interquartile range below it. Right? So I don't know what these would be. So this would be what? The interquartile range is 30. So that times 1.5 is what? 45. So we would go 45 below this, -5, 45 above this. See if I can do the math in my head correct here. And that's how we kind of come up with that. Right? it's pretty basic math. Once I have identified what those quartiles are, it's just a little bit of math to create this box and whisker plot. So the reason why we like to do this is because, you know, we're not going to use these a ton, so I'll just briefly explain. You know, what this would tell me is that there isn't as much data below, right? The data below the median is more centered really close to it. And then the data above the median, right, is kind of a little bit more spread out. The values that I see are kind of a little bit more spread out, right? But the real important thing that this tells me is when I set this upper and lower limit, you know, I can think about, if I wanted to, I could plot every single observation I have, right? So let's say this variable is, I don't know, I was going to say IQ, but these numbers are a little bit low. Let's say it's your score on some test, but the test isn't 0 to 100. It's got this huge range of values, right? You could plot every single person's test on this line, right? Every data point would just get plotted wherever its value was. And if I ever see data points, right, and I might see some right here, any data points that are outside that lower and upper limit, we can say these are identified as outliers, right? They're so far outside the range of where most of the data is that either something weird was going on when I recorded it, or it's just a very abnormal kind of observation or a value for the observation that I could see, that anything outside that lower and upper limit, we're going to say we can use this as verification that they're outliers. And occasionally, depending on the work we want to do, we'll actually say this is justification for leaving this outlier out of my analysis, right? It's so far outside the normal range of data that if I use it in calculating my mean, or it's going to really screw with that mean, right? Or it's really going to kind of alter that variance calculation, right? So we can use this box and whisker plot to justify not including certain observations or defining them as outliers, okay? Like I said, I only go over this because I know that you might see this in other courses, these box and whisker plots. Any questions on that? Shouldn't be too bad. What can I do? I can go to, hopefully this makes it a little bit more seamless jump. I lied. Waiting for the screen here in class. There we go. So any data outside that is kind of an outlier. This is called the Q test. I always like this meme, so please don't reject me as an outlier because you are the Q test, because the Q test would reject outliers. So I don't know. Good little meme for us. But then, like I said, you might see this in other courses, and it's a good way of identifying these extreme values, okay? So, you know, I kind of did the same kind of spiel with the tables and graphs. Up to this point, we've only looked at one variable, so let's look at the relationship between two variables with a scatter plot, right? That's kind of how we did it. Well, now we're going to look at some statistics that measure the relationship between two variables. So, check the time. So, you know, we think that, you know, there's some variable X and some variable Y. This could be education and income, years of education and income. This could be, I don't know, height and weight. This could be whatever two variables we're interested in. And we think about when one of them goes up, right, as height goes up, maybe somebody tends to weigh more, right? That would make sense. So we think that the other variable could go up, could go down, or maybe it doesn't change at all, right? So we have two measures of whether or not two variables move in the same direction or kind of move in opposite directions, or whether they're just not related at all. So those two measures are the covariance and what we'll call correlation, or probably more specifically, the correlation coefficient. Okay? So we're going to talk about how we calculate the covariance. And then from there, once we have the covariance, it's actually pretty easy to get that correlation. Okay? If I can get going, there we go. So we have these two variables, right? And what we're going to do is use this formula here. So it's a little bit different than what we've had before because we now have two variables. Okay? So the first thing we're going to do is calculate the mean for the X variable and the mean for our Y variable. Right? We'll then look at every single observation. We'll go and say, okay, how far away, or what was the difference between that observation's value for the X variable and the mean for X? And how far away was that observation's value for the Y variable from the average Y? Right? I will then multiply those two differences together, do that for every single observation, and then, right, the summation sign, add them all up for every observation. Finally, I'll divide by n, okay, or the number of observations in my population data set. The sample is going to be the exact same, but instead of dividing by n, we divide by n minus 1. So nothing real different from kind of calculating a regular variance, right? But this covariance is going to operate a little bit different than our variance. So maybe a good interpretation of the covariance is, on average, right, what is the, what's a good way to throw this? So on average, what is the distance from the mean that both of these variables are, right? And one interesting thing here is the values that we add to our numerator don't have to be positive anymore. We're not squaring them, right? So it's saying, on average, do both of these observations lie on the same side of the mean or on different sides? Because if they're on the same side, let's say I have the height and weight example. Let's say I have someone who's above the average height and above average weight. Well, that would be an observation that's evidence, right? If I'm above the mean on both of these, it's a positive times a positive. Or that was evidence that height and weight tend to be on the same side of the average, right? So that when height is higher, so is weight, right? When one is above the mean, the other also tends to be above the mean. If we had an observation that was evidence that these two things are on different sides of the mean, right? Maybe I have someone who's below average height, but above average weight. Well, that is an observation that's evidence that, well, when height tends to be lower, weight tends to be higher, right? Now, we're going through every single observation and then essentially taking the average of kind of whether or not these two things fall on the same side of the average for each variable, right? So it gets a little bit more complicated. If it's positive, right, we end up going through this computation and we find a positive covariance. That means that there was more observations that showed that both of these variables tend to be on the same side of the average, right? If it's negative, what that's telling us is overall, kind of we found that across all these observations, these variables tend to be on opposite sides of the average, right? Or that when one is higher, the other tends to be lower. And if it's pretty much zero, we found that there's no relationship, right? So there was some observations where they were on both on the above the average. There was some observations where they were on either sides of the average, right? And then we took kind of the average across every observation. They pretty much cancel each other out, right? Because there's going to be some negative values and some positive values in our numerator now. And if we get zero, it just means there's no real relationship between these two variables. Okay? So how does this look like in practice? So let's say I have a height weight data set, right? So we'll just go through the first 4 observations. I think I had like 44,000 here. You can get a bunch of data from the CDC. So I found the mean height and the mean weight in this sample data set, okay? What I'm gonna go through and do for every observation is say, well, how much does this first observation's height deviate from the average? Well, I've got the mean or the average down here. So 70 minus 63, write that number down, right? This person was above average height, quite a bit above average height. This person's weight was actually below the mean, right? If I look at that weight and subtract 187, I get about -8. So this one observation was evidence that height and weight are on opposite sides of the average, right? Or that this was one observation that provided evidence that when someone's taller, they tend to weigh a little bit less. Now that's just one observation. So when I multiply these two, a positive times a negative, I get a negative value there, right? That one observation was evidence that there's a negative correlation between height and weight, right? But if I go down to the next observation, well, this person was just barely below the average height, but they are below the average weight, right? So that when I multiply a negative times a negative, right, both these things are on the same side of the average. They were both below it. This observation is evidence that there is a positive correlation between these two variables, right? They tend to be when height is higher, so weight tends to be higher as well, or said differently, when weight is lower, when height is lower, weight also tends to be lower. I then go to the next observation. This person's quite a bit below the average height and quite a bit below the average weight. So we get kind of a positive value, right? They're both on the same side of the average. We would go through and do this for every observation, right? And we will have some observations that provide evidence that these two things are on different sides, but more of these observations are providing evidence that they tend to both be on the same side of the average. Okay? So once I add all these up and then divide by the number of observations I have, I get kind of, what is this average relationship between these two variables, right? Across all the observations, I'm taking every single observation into account. What's the average kind of this relationship between X and Y? Okay. So if I do this for this example, I'm pretty sure, yeah, this is kind of an intuitive one. We probably could have guessed the covariance between height and weight is positive, right? Someone who's 5 feet tall as opposed to 6 feet tall is probably just going to weigh less, or someone who's 6 foot tall is going to weigh more. Right? We kind of know that intuitively. But sure enough, we go through and calculate this across all 44,000 observations. We get this positive covariance. Okay? Any questions kind of over this process here? Kind of get what we're getting at here. That's not a perfect measure, right? In fact, if we think about what does this 76 value actually tell us? Right? I don't know. I mean, what's the units, right? I was taking height and multiplying it by weight. So my units were inches and pounds, but I've multiplied them. So like the units of this covariance are inch pounds. I don't know what the hell that is. Is it strong? Is it not strong? As a covariance, should it be as high as like 1,000? It's kind of hard to determine, right? Because I've got these weird units and I really can't compare covariances across different types of relationships, right? I can't compare the relationship between height and weight because it's inch pounds with maybe years of education and income, which would be what, year dollars, right? There's no way to compare these things. So the covariance is a good start. It tells us about what this relationship is, the sign, right? We can tell if it's positive or negative, or zero if there's no relationship. But to be able to compare the relationships across different types of variables, we have to go one step further, okay? Whoops, yeah. So we're gonna scale the covariance by dividing by the standard deviation of each variable. So the way we're writing this covariance is sigma, and then whatever two variables we were looking at the covariance between. So sigma xy is the covariance, right, between whatever x and y variable we're looking at. If we divide by the standard deviation of each variable, and kind of think about it as if I've got inch times pounds on top, well, I'm dividing by something that has the units of inches, so that would cancel. And then I'm dividing by something that has the unit of pounds, so that cancels as well. So I'm basically getting a unitless measure, right? I'm scaling this and I'm getting rid of my units. Okay? Now, we don't have to exactly understand kind of the mathematics behind why this is going to be, but I'll try to give you somewhat of an idea before we leave today. This correlation coefficient, once we divide by the standard deviations of each variable, it has to be between 1 and -1, right? So we get this nice property where it's always going to be between 1 and -1. 1 being the strongest positive relationship you could ever see, -1 being the strongest negative relationship you could ever see between two variables. Right? It's also going to be unitless, which we talked about, which is kind of nice for us. Okay? So now with this correlation coefficient, I can compare across examples and say, if I've got a correlation coefficient between height and weight, that is, I don't know, 0.4, and the correlation coefficient between years of education and income is 0.7, I can say the relationship between education and income is stronger than the relationship between height and weight. Okay? So the closer to 1 or the closer to -1 tells you evidence that there's a stronger relationship. And then the sign is the same as the covariance. If it's positive, that means as x goes up, y tends to be higher as well. And then if it's negative, as x is lower, y tends to be kind of higher, right? They move in opposite directions. So I'm trying to give you some type of an idea behind why this is the case, why this has to be between 1 and -1. Let's just break down the equations and hopefully we can get a little bit of an idea without having to understand like a true mathematical proof. Right? So what I'm doing is I'm taking that covariance and I'm dividing by the standard deviation of each variable. right? So this covariance, if I write this out, looks something like this. So that's my numerator. I'm then going to divide this by the standard deviation for each one. So this is like the square root of, what did we have? The sum of x minus the mean squared over n minus 1 times the square root of the sum of y minus the average y squared divided by n minus 1. So you can kind of see where things are going to cancel. This isn't I'm violating a lot of mathematical rules here, but kind of giving you an idea about why this has to be between 1 and negative 1. You can kind of see here, everything's being divided by n minus 1, so that is going to kind of cancel. I've got some squared thing going on there. That's not exactly correct mathematically, but you can kind of see how that would cancel. And now I've got some of the difference for the x and its mean, some of the difference for y and its mean. Kind of have that going on up there. Well, you can kind of see how that's all going to cancel to where I get 1, right? Now, like I said, everything's not canceling, right? But the idea is that somehow the standard deviations, when we divide by them, they're scaling that covariance so that it at most could be 1 and at most would be negative 1. But that's not overly important, like you understand, like we go and find the mathematical proof. Once we know that that's going to be the case, it's pretty easy to work with. The closer to 1 means it's a stronger positive relationship between these two variables. The closer to negative 1, the stronger a negative relationship that exists between those two variables. Okay. Got a couple minutes left here. So, oops, let's see if this is more. We can get here. All right. So if I had that height weight data, I had that covariance, I could calculate pretty easy in Excel the standard deviation, right? If I've got this column of data, I just use that STDEV.S equation, find the standard deviation for height, standard deviation for weight, and now it's just a matter of plugging those values in, right? So these correlation coefficients should be pretty easy to calculate, right? Once we have the covariance, once we have the two standard deviations, very easy to find that correlation coefficient or that correlation. Okay. Now, is 0.45 strong? Well, I don't know. It's halfway between 0 and 1, right? If 1 is the strongest and 0 is no relationship, I could say like this has kind of like an average relationship, right? It's kind of in the middle there. It's not the strongest. It's not the weakest. But I really can't, you know, what is really strong? I mean, usually once you kind of get into thinking about what a strong correlation is, we like to see things high as like 0.7 or 0.8 as evidence of a very strong relationship, but it doesn't matter. We can at least compare this relationship to other types of variables, right? The relationship between education and income, the relationship between age and, I don't know, some measure of cognitive ability or something like that, right? So this is kind of, I think, pretty easy. Once we have the covariance, it's pretty easy to get the correlation. Any questions on this? All right, I think I might end here. We'll kind of revisit this. There's some, you know, sample questions that just give you some different numbers. Might be good to kind of work through these on your own. I'll post an online quiz once I get back to my office. It'll have a question that looks like this, but hopefully, you know, once we have this as our template, if I give you the covariance and the standard deviation, it's really just a little bit of math, right? Just plugging those values in. Kind of maybe briefly mention this idea. I've got a video that we might watch on Friday, short little video, and then we'll jump into probability, okay? So start working on that Excel and that Connect assignment. It's due next Friday, both of them at the end of the day. We'll have an online quiz I'll get posted when I get back to my office. That's due before class on Friday. Other than that, if you have any questions, email me, and I'll see you Friday.